Hello everyone. My name is Jacob, and I'm going to be talking about the spectral sparsification of hypergraphs. And this is joint work with Michael Karpolov, Robert Krautgamer, and Yuichi Yoshida. So first of all, what is graph sparsification? Graph sparsification is the act of taking a potentially dense input graph and reducing its edges by taking some subgraph and reweighting it into a much smaller graph in such a way that it maintains some crucial properties of the original graph. So in particular, cut sparsification, which was introduced by Benzer and Carter, means that the sparsifier, which is the output graph, should retain the same cut structure as the original graph. So the size of each cut should be the same. And then spectral sparsification is a generalization of this, introduced by Spillman and Tang, which says that the quadratic form of the graph Laplacian should be the same up to some small multiplier 1 plus or minus epsilon. Now, analogous concepts can be defined for hypergraphs as well. Cut sparsification in particular is very natural. You can also define the cut structure of a hypergraph, and you can say that the cut sparsifier must have the same cut structure as the original graph. Now, in order to define hypergraph spectral sparsification, we should extend the notion of the quadratic form of the Laplacian to hypergraphs, which has been done in the literature, and this is the formula for it. So whereas in ordinary graphs, we would sum xu minus xv squared for all edges, here for all hyperedges, we sum the maximum of u, v, and e of xu minus xv squared, which we call the energy of the hyperedge, because of course, each hyperedge could contain many more than 2 vertices. And so a big difference is that this is actually a non-linear function, even though we do call it the quadratic form of a hypergraph. But it has many nice properties. For example, it generalizes the ordinary graph Laplacian. It also contains the cut structure of the hypergraph. So you can just query this function at a indicator vector for a set, and you will get the size of the corresponding cut. It has many applications and has been highly studied in recent years. And so based on this, one can define the notion of a hypergraph spectral sparsifier by just saying that this quadratic form of the sparsifier should be approximately the same as the quadratic form of the original hypergraph. And so indeed, this has been studied also in recent years, both cut and spectral sparsification of hypergraphs. In particular, for cut sparsification, the recent exciting work of Chen, Kana, and Nagda achieves a nearly linear size. And for spectral sparsifications, we're not quite there, but our result is an approximately n times r sized spectral sparsifier, where r is the arity of the graph, so the maximum size of a hyperedge. Now we also get a related lower bound, and one could ask, what is a lower bound in this setting? It's actually quite obvious to see that at least n hyperedges are required. One can easily construct examples where you would need n hyperedges just to maintain connectivity, which is crucial. However, one could ask, why are we even using this method of taking a subset of the original hyperedges and reweighting them? Why not take new hyperedges that didn't even exist in the original graph? Or why not take just ordinary edges? Or why not take any other data structure? And in particular, this is interesting for hypergraphs because unlike in ordinary graphs, to take n hyperedges, it actually takes n times r bits. So one could hope that with a more clever technique, it's possible to get the bit complexity of a data structure compressing the spectral or cut properties of a hypergraph down to order tilde n bits, as opposed to order omega tilde n times r bits. But actually, we proved that this is impossible for most settings of the parameters. We proved that omega n times r bits are actually required to compress even the cut structure of a hypergraph of RTR, no matter what data structure you use. But we'll get to this later. So let's start with our construction for hypergraphs. And indeed, we use a very common technique for constructing spectral sparsifiers, which is importance sampling. So importance sampling just means that for each edge or hyperedge of the input graph or hypergraph, we set some probability, PE, and then we independently sample with this probability. And for each edge or hyperedge that makes it through the sampling process, we upweight it by something that is inverse proportional to its probability of being sampled, which effectively means that the sparsifier will be an unbiased estimator for the original graph. This is, for example, the technique that was used by Spillman and Strabasto for spectral sparsification of ordinary graphs, where they chose the importance measure to be the effective resistance of the hyperedge. And if we have this, basically what we need to prove is that this random quantity, q tilde x, concentrates around its expectation for all x simultaneously. Now, we don't actually want to deal with effective resistances. It is possible to define effective resistances in hypergraphs, but it's difficult to handle. And so we make several simplifications to the input hypergraph so that we can use a simpler importance measure. So first of all, we assume that the hypergraph is deregular. This is a fairly simple simplification. I'm just doing it for the purposes of this talk, and the proof is actually more or less identical for irregular graphs, albeit with heavier notation. We also assume that the input hypergraph is R uniform. Again, this is a fairly basic simplification to make, and there's a simple trick to handle it, which we describe in our paper. And the most non-trivial simplification is that we assume that the input hypergraph is actually a good expander. So first of all, what is a good expander for R uniform hypergraphs? For ordinary graphs, we would expect to call something a good expander if it has expansion that is constant, or in the worst case, inverse polylog n. But this is actually not the case for hypergraphs. Here, the best we can hope for is to have expansion 1 over r, and this is because the degrees of the vertices are blown up by a factor of r relative to the number of edges that exist in the graph. So actually, if you take a random cut, it will typically have expansion at least 1 over r. So we can't, at most 1 over r. So we can't really hope for better expansion than that. And so we define a good expander to have expansion at least omega tilde 1 over r. And then we can use an equivalent of Chigurh's inequality for hypergraphs to relate the quadratic form to the variance of the input vector x. And we're going to be using this in our analysis. And the reason we can assume that the input hypergraph is a good expander is due to some sort of expander decomposition argument for hypergraphs, which is far from trivial, but I don't have time to go over it in this talk. So I encourage everyone to look at our paper. All right, so what is our proof plan? We're going to use importance sampling. Thanks to the fact that we're dealing with a regular expander, we can actually use uniform sampling, which is really nice and convenient. For irregular graphs, this formula is slightly more complicated, but not significantly more complicated. And we get a nice small sparsifier as a result. Actually, for regular graphs, we get a linear size spectral sparsifier. Unfortunately, for irregular graphs, this is slightly worse. So this is where our factor R comes in. And again, what we need to prove is that this random quantity concentrates around this expectation for all x simultaneously. So what is going to be our proof plan? Typically at this point, for ordinary graph sparsification, people use some linear algebraic tools for analysis. So something like matrix Bernstein, which can prove simultaneous concentration for all values of x if q was a linear operator. But unfortunately, in our case, this is not true. The hypergraph quadratic form is highly nonlinear, and so we have to resort to some more basic techniques, which is going to be direct chaining. So what we're going to do is first discretize x to some epsilon net. So this means that now we have to only deal with finitely many values of x tilde. And because this is the concentration of a random variable around its expectation, we can simply use typical concentration inequalities, such as Chernoff bounds, to prove this formula for a specific value of x tilde. Now, once we have that, because there are only finitely many values of x tilde, we can use union bounds to bound it simultaneously over all x tilde, and this will imply a result simultaneously over all x. So let's take a closer look at this Chernoff bound that we're going to use. So first of all, we can assume that x is centered and has variance 1, just because the equality that we're trying to prove is the inequality that we're trying to prove is shift and scale invariant. And by our Cheeger's inequality, this is going to mean that that the quadratic form is at least 1 over r. All right. So what will our Chernoff bound look like? This q tilde x is a random variable, which is actually the sum of many independent random variables. So this is a perfect candidate for applying Chernoff bounds. And if we actually write down all the details, we'll see that the expectation, which is q of x, cancels out due to our lower bound, thanks to the hypergraph Cheeger. And what we're left with in the exponent is just this term which relates to the maximum size of each random variable, right? This is one of the terms in the Chernoff bound, which is going to dictate the power of our Chernoff bounds, is how large can each individual independent random variable get. And unfortunately, we find that they can get pretty large. So if we just look at this bound, this is very weak. That formula highlighted in red can get as large as a constant for some hyper edges. And unfortunately, in that case, this bound on the probability of failure is way too high. There's no rounding scheme that is sufficiently coarse to be able to take a union bound over this probability. So what we're going to do is we're going to try to get a more precise Chernoff bound by categorizing the edges. So we call this formula d times the maximum of xv squared over a hyperedge, the power of that hyperedge, because this is what is going to dictate the strength of a Chernoff bound, which involves that hyperedge. So we simply define categories of hyperedges based on the power. So EI is the set of all hyperedges with power approximately 2 to the minus I. And this will lead to the following Chernoff bound. This is exactly the same thing as before, except for the fact that we're not looking at the entire hypergraph, neither the sparsifier nor the original input hypergraph, but we're reducing both to the sub hypergraph that is that only uses hyperedges in the ith category. And indeed, we get the exact same formula on the right-hand side, again with the exception that instead of maximizing this over all hyperedges in E, we only maximize it over all hyperedges in EI. And this is a crucial difference. By definition of EI, we now get this very nice upper bound of exponentially in minus 2 to the I. This is much more powerful, and now we actually have a hope of getting sufficiently coarse epsilon nets to combine this Chernoff bound with a union bound. So, okay, what should this rounding, this epsilon net look like? So you want to round x to some x tilde of I, right? This is now a specific rounding scheme for the ith category. We have a different rounding scheme for each category. And so this gives us the advantage that the rounding scheme should only respect the energy of a hyperedge if that hyperedge is in the ith category. We don't need to worry about any of the other hyperedges, which is very nice. And the bound on the number of possible discrete vectors x tilde of I should be exponential in 2 to the I, right? So that our union bound should exactly balance out with our Chernoff bound. And in the end, we should be able to say something meaningful what the probability of concentration simultaneously for all x. All right, so with these specifications in mind, let's see what kind of a rounding we can construct. So here we have plotted all the, or most of the vertices in the vertex set of our hypergraph with specifically the vertices in some hyperedge E shown in darker color. So what should our rounding do? So the energy of the hyperedge E is governed by these two most extreme vertices, right? This is just a squared stretch between them. And so really what we want is for the distance between those two vertices not to change too much. And one additional piece of information that we have is that we are in the ith category. E is in the ith category, and therefore we know that the most extreme vertex has a value at least 2 to the minus I over 2 in this plot. So we can use this information to our advantage. And we can just say that anything that is significantly smaller than that, so an epsilon factor smaller, is deemed to be unimportant. And everything that is not that much smaller is deemed important. And what we can do is we can save a lot of, well, we can reduce the size of the rounding scheme a lot by just rounding all unimportant vertices to 0. Now for important vertices, we're going to round them very carefully. How carefully? Well, it doesn't really matter. So carefully that in the analysis, it won't really matter. It's going to be almost as though we didn't round them at all. But this is still going to be fine, actually. And we're going to round unimportant vertices to 0. So one can simply see that because we know that at least one of the extreme vertices of E is important, is very important, actually, an epsilon factor larger than any unimportant vertex, we know that even if the other side of this stretch is unimportant, the change in energy resulting from this rounding is not going to be very large. And of course, if both sides of the stretch are important, then it's going to change almost not at all. So this actually satisfies our first condition, that it preserves the energy of each hyper edge in EI. What about our second condition? How many different possible rounded vectors are there? Well, crucially, we can count the number of important vertices globally, right? We know that the variance of the vector x is 1, and so the number of important nodes is at most 2 to the I. And so based on this, we can very simply calculate that the number of possible vectors x tilde of I is at most exponentially that number, right? Because we just have that many non-zero coordinates, and we only have to carefully encode these coordinates. Everything else is 0. So there we have it. This satisfies all the requirements for a rounding scheme. And this actually concludes the proof. So let's just quickly go over what we did. We divided the hyperedges into categories. And instead of proving concentration globally, we proved concentration for each category, which we did with a chaining argument combining Chernoff and union bounds, and specified a specific rounding scheme for that category. And all right, and the remaining time, I'm going to talk about our lower bound. So just to recall, this is our lower bound result. We're saying that no matter what data structure you use, it's information theoretically impossible to compress the cut structure of a hypergraph of arity R to fewer than n times R bits. So actually the result of Chan, Khanna, and Nagda is nearly optimal due to this lower bound. So how do we do this? We're going to use a reduction from string compression. So string compression is the problem of compressing an n-bit 0-1 string in such a way that you can recover subset sum queries. So a query would look like this. I would just look at a subset of the coordinates and say, what is the number? How many ones are there? And in this case, the answer is 3. And it's pretty intuitive that in order to compress such a string, we need at least n bits, or at least omega n bits, because you pretty much have to know the entire string. But there's actually a known result on this. So even if you allow relatively large additive error of epsilon times n for some small constant epsilon, it's impossible to efficiently compress such a string. And it's very important to note that the result holds over only most inputs. So it doesn't have, like, even if you don't have to compress all input strings, you can think of the input string as being random and compress only a random input string. The result still holds, but you have to answer queries on all subsets, not just most subsets. It's trivially easy to answer subset sum queries on most subsets just by statistically answering, but the really interesting queries are the ones with the imbalanced subsets, so the ones that contain more ones than zeros. And this is exactly analogous to spectral and cut sparsifiers. The interesting cuts are the ones that are very small or very large. So let's see, how are we going to encode, how are we going to reduce the string compression to cut sparsification of hypergraphs? And we're going to use a compression that goes through Rouge-de Samarity So we call it TA Rouge-de Samarity a graph that is composed of T induced matchings of size A. So for example, here's one. This is a graph that consists of 5 induced matchings of size 3. It's not a very interesting construction, but there are very interesting constructions of Rouge-de graphs that are much more efficient. And how are we going to use this to encode a string? So first of all, the length of our string is going to be the number of edges in this graph. And for simplicity, we're going to assume that the string is indexed by edges of the graph. So we can just think of the input string as 0-1 labels on the edges of this Rouge-de graph. So we can very simply encode the string into the graph by just dropping the edges labeled by 0. So we only retain the edges that were labeled by 1. So we get this subgraph. And now we're going to convert this into a hypergraph in, again, a very simple way by just taking each vertex on the top side of the bipartition, so on the P side, and making it into a hyperedge along with all of its neighborhood. So each hyperedge is going to consist of a single vertex on the P side and possibly multiple vertices on the Q side. And we call the P side vertex the root of the hyperedge. And so here are two pictured. Not all of them are pictured, obviously. And one can also note that we get a nice bound on the arity of the hypergraph. So this is it. We have now encoded a string into a hypergraph. What do we do once we get a subset sum query? How do we decode a query? So suppose we get a query which is just a subset of the hyperedges. Subset of the edges of the original Rouget-Samariti graph, because our string is indexed by the edges of the Rouget-Samariti graph. Now, for simplicity, we're going to assume that the query entirely resides in a single induced matching. This is not, of course, the case in full generality, but one can simply solve this problem, which I'm not going to go into the details of. But let's take a look at this picture. So here is our original graph. Here is the induced matching, and the query is a subset of the edges. So we're basically asking how many 1 labels are there on these edges and how many 0 labels. And now we claim that one can actually answer this query by only knowing the cut size of this set S in the hypergraph. So S is defined as containing all the vertices corresponding to query edges in P and all the vertices outside of the support of M in Q. So how do we take the cut size of this S and deduce the answer to the subset sum query? Well, let's see what the size of the cut is. And for that, we're going to categorize the edges. What kind of edges can cross this cut? Well, there's type 1 edges whose root resides in one of the vertices corresponding to a query. There's type 2 edges whose root resides still in the matching, but not inside the query. And the type 3 edges, which just reside outside of the matching entirely. And let's count all of these different hyperedges. So actually, a type 1 hyperedge is going to be the most informative for our case, because a type 1 hyperedge crosses the cut if and only if the corresponding matching edge in the Rouget-Samariti graph is labeled by a 1. If it's labeled by a 1, then of course there's a neighbor of the root vertex which is on the other side of the cut. But if it's labeled by a 0, then of course that edge is dropped. And because of the induced nature of the matching, no other neighbors of the root reside on the other side of the cut. So actually, in this case, the hyperedge is not going to cross the cut. And so we can say that the number of type 1 edges that cross the cut, type 1 hyperedges that cross the cut, is exactly equal to the answer to the subset sum query. So this is great. Unfortunately, then there are type 2 and type 3 hyperedges that spoil this. But let's see if we can do something about that. So what about type 2 hyperedges? Well, actually, again, because of the induced nature of the matching, we can say that almost all of the type 2 hyperedges cross the cut. So unless the root vertex has extremely low degree, it's going to have multiple neighbors, and all but one of those neighbors are going to reside outside of the support of M, and so inside the set S. And with some basic assumptions on the original Rouget-Samariti graph and some basic assumptions on the input string, which we're allowed to have, we can say that nearly all of type 2 hyperedges will cross the cut. And so this is a predictable quantity to within a small additive error, and we can just subtract it off. And what about type 3 hyperedges? So this is the most interesting case. Actually, we don't know how many type 3 hyperedges will cross the cut. This is entirely dependent on the specific construction of the Rouget-Samariti graph. However, what we do know is that this is a predictable quantity. Unlike type 1 and type 2 hyperedges, type 3 hyperedges are defined entirely independently of the query, right? They are defined, both the hyperedge itself and whether or not it crosses the cut is defined in a way that is independent from the query. It's dependent only on the string. So we can actually store this quantity in the data structure if we want to, or we can use its expectation as an estimator, and that will also be that will also be very close to reality with very high probability. So this, we don't know how much it is. This is based on the specific construction of the Rouget-Samariti graph, but it is a predictable quantity. So we can actually calculate this as well and subtract it to within a small additive error. And so what we can do is measure the cut size of this set S, if we had a cut sparsifier for our hypergraph, and simply subtract the number of type 2 edges that cross, subtract the number of type 3 edges that cross, and as a result, we get an approximation to the number of type 1 edges that cross, which is exactly equal to the answer to the subset sum query. And here we have some additive error terms, but that is still fine by the definition of string compression. So with this reduction, we essentially get this very generic theorem, which is stated in terms of the existence of Rouget-Samariti graphs. And any Rouget-Samariti graph will imply some lower bound for the cut compression of hypergraphs. And one can instantiate it with any of many different Rouget-Samariti graph constructions. In our opinion, the most interesting one is to use the construction of Fisher et al., which tells us that even for constant epsilon, it's impossible to get a better compression of the cut structure of a hypergraph than the result of Chen, Khan, and Nagda for a large range of variables R. But even for larger R, one can get similar statements using other constructions of Rouget-Samariti graphs. And if new Rouget-Samariti graphs are found, they will immediately imply new lower bounds on the bit complexity of the compression of the cut structure of hypergraphs. So to summarize, we have this construction for order tilde NR sized spectral sparsifiers for hypergraphs. We have a lower bound which has a bit complexity of order tilde NR, even for cut sparsifiers, which is tight. And finally, coming soon, hopefully, we have a new result which will give us a nearly linear side spectral sparsifier. Thank you for your attention.